Yeah, okay. We're just going to very quickly finish up chapter 18. Uh, this last thing about Dalton's Law is something that's not found in the chapter, but the real version of Dalton's Law is this formula right here. I'm going to put a box around it. We said that pressure is created by the number of particles hitting the container wall a certain amount of force. So the kinetic energy comes from the thermal environment. So in a gas mixture, they're all sharing that thermal environment, so they all have the same average kinetic energy. So we don't care about the identity of the particles, it's the number of particles that create the pressure. So therefore, the partial pressure is created by the percentage of particles that happen to have that identity. So this ratio of how many particles you have for a certain gas compared to the total in the mixture is something they call the mole fraction. And Dalton's law is really partial pressure of any gas is equal to the total pressure times the mole fraction of that gas. And the mole fraction is, again, the moles of that gas divided by total moles in a sample. So suppose we had this. Suppose we had a mixture of, let's say, 52 grams of oxygen, and we're going to mix that with 8 grams of carbon dioxide. And we hook up a manometer, and we find out that the total pressure of that mixture comes out to be 762 millimeters of mercury. They want to know, what is the partial pressure of oxygen in that sample? All right, so we need to know the moles of oxygen and the total moles in the sample in order to be able to do that. So we're going to convert 52 grams of oxygen, and we know that for, if we look this up on the periodic table, that there are 31.996 grams of oxygen per 1 mole. So let's see how many moles that is. That's 1.6. We should round to the even number. It comes out to be 1.625, but we're going to round to 1.62. Round down to the even number on that one. And that's going to give us moles oxygen. And then we have to do the same thing with carbon dioxide. 8 grams carbon dioxide. And we look up carbon dioxide on the periodic table, and we get 44.009, I think. 44.007. Wow, has it been really that long? Maybe I did a problem with the calculation here. Plus 2 times 15.998. No, it's 44.007. Wow, I am forgetting things since we are not in school. Thought it was 44.009. Anyway, so this comes out to be 0.18 moles of carbon dioxide. Okay, great, good for us. All right, so now we can do mole fraction. All right, mole fraction of oxygen is equal to moles of oxygen divided by total moles in the mixture. So moles of oxygen plus moles of carbon dioxide. We substitute in. And we get 1.62 divided by 1.8. We get a mole fraction of 0.90. So now to get our final answer, we can use Dalton's law. Partial pressure of oxygen is equal to total pressure times mole fraction of oxygen. Total pressure was 762 millimeters of mercury. And oxygen makes up 90% of the particles, so it's going to make up 90% of the pressure. (686 millimeters of mercury). All right. All right, last part of the chapter. Something called Graham's law. And we focus in chemistry on Graham's law of diffusion, but it's actually this law governs both the process of diffusion and the process of effusion. They're not too different from each other. We'll talk about both of them. But again, we're going to focus on diffusion here. Random scattering of gas particles, which means that how long will it take for if we mix gases together, how long will it take for the gases to mix uniformly and spread out? We know that they all share the same kinetic energy, but therefore 1/2 mv squared equals kinetic energy. So if you have a large mass, you have a lower velocity, it's going to take longer for your particles to diffuse. And if we go and we take a look at, before we do any calculations with this, what's the difference between diffusion and effusion? Really not much of a difference here. Diffusion, we're mixing two gases together. With effusion, you have a gas and it's permitted to escape through an opening into an area of lower pressure. So sometimes the size of the opening can be a factor, so there is a slightly different calculation for effusion, factoring in the size of the opening. But with diffusion, again, we're just talking about mixing the two gases together. Bromine is an orange liquid. This is just a picture showing how bromine, when it vaporizes, the gas spreads out over time to fill up the container. And we said that this is derived from the formula for kinetic energy. How long it takes for something to spread out and scatter is going to be based upon its kinetic energy. So high mass particles are going to have lower velocities. So we can set the two different particles equal to each other, since they have the same thermal kinetic energy average, with 1/2 mv squared for the one particle equal to 1/2 mv squared for the other particle. And then we can solve for the ratio of velocities compared to the ratio of the masses. They're inversely related. High mass has a low velocity for diffusion. Low mass has a high velocity for diffusion. I'm going to rewrite this, though, in human form. All right, so Graham's law. Now, in this case, V stands for velocity. And you'll get the right answer regardless of how you set this up, as long as you're consistent with the way you substitute in. But I tend to like to put the faster particle in the numerator and the slower particle in the denominator. So when they do V1 over V2, velocity 1 over velocity particle 2, I'm going to make this the light one. So let's say that this is the high velocity particle and that this is the lower velocity particle. And that's going to be equal to the square root of curvy M2 over curvy M1. Now curvy M stands for molar mass. And the formula for molar mass is grams of the material divided by moles. So there's an inverse relationship between speed and molar mass, and we know that from chapter 15. Now, how long will it take the particle to scatter and fill the container? Well, the heavier particles take longer. So if we do T for time, we could also say that the time for the diffusion is going to be T2 over T1. In other words, velocity and mass are inversely related. If you have a low velocity, you're looking at high mass. If you have a high velocity, you're looking at low mass. The relationship between velocity and time for scattering is going to be inverse as well. If you have a low velocity, it takes a lot of time. If you have a high velocity, it takes very little time to scatter. And the relationship between molar mass and time for scattering is going to be directly proportional. That if you have a heavy particle, it takes more time. So there's really two types of problems that they give you with Graham's law at this stage. And we'll take a look at them. All right, first one. We have a mixture of neon and carbon dioxide, and we're going to allow them to diffuse. How much faster is the neon gas particle than the carbon dioxide gas particle? Okay, we can do that. Copy. Oopsie poopsie. Let's paste this. All right, so neon and carbon dioxide. So first of all, we look up the molar masses. Molar mass for neon. So I'm going to look neon up on the periodic table. I happen to have my handy dandy periodic table here, and we're looking at a mass of 20.179 grams per mole. And then we'll look up the molar mass of carbon dioxide, which we did in the last problem, is 44.007 grams per mole. So we know by looking at the masses that this one is going to be faster, and this one is going to be the slower particle. So when I substitute in, I do V1 over V2, I want to put the faster particle in the numerator, simply because when you solve, you get values greater than 1 as your answer, and the values will make more sense. If you invert this, as long as you're consistent, you'll still get the right answer, but the interpretation of the results is really weird. So I'm going to ask you not to do that. So we're going to have the velocity of neon over the velocity of carbon dioxide. And when they say how much faster are they, then really what we're doing is we're solving for this ratio. So we're going to do the molar mass of carbon dioxide over the molar mass of neon, because they're an inverse relationship. And that's going to give us the square root of over 20.179 grams per mole. So again, this ratio that we're solving for is going to be equal to the square root of, let's do 44.007 divided by 20.179, and we get 5 sig fig, so 2.1808, and then we'll take the square root of that. And we get 1.4768 is our answer. Okay, so what does that answer mean? What it means, your interpretation of this would be that neon is 1.4768 times, or you could write the word times instead of x, times faster than carbon dioxide. Now, at the AP level, we could actually calculate the speeds, but at this level, they're not asking you to. They're just asking you to compare the two speeds. So we know neon is faster than carbon dioxide because it has a lower mass. How much faster? About 1.5 times faster than carbon dioxide. The second type of question, they may ask you, how long? How much time does it take? So let's look at the next question. Ammonia and carbon dioxide are allowed to diffuse. The ammonia takes 12.6 seconds. How long does the carbon dioxide take? Okay, there we go. All right, so again, I'm going to start with molar masses here. So the molar mass of ammonia. So we look up nitrogen and hydrogen. 3 times 1.008 for the hydrogen plus 14.007 for the nitrogen. We get 17.031 grams per mole. And we look up the, again, carbon dioxide, which we already know, is 44. Oopsie poopsie. Why did that happen? That's weird. Probably because my knuckles hit it. I hate being left-handed. 44.077 grams per mole. Okay, great. So now we can set up this relationship. Molar mass of the heavier particle versus the molar mass of the ammonia. And we know that that's going to be equal to T2, which is the heavier particle. So the time for the carbon dioxide over the time for the ammonia. They're direct proportion. So now we can substitute in. Well, actually, I'm supposed to solve for time for carbon dioxide first. So time for carbon dioxide is going to be time for the ammonia, if we're doing the algebra here, times the square root of molar mass of carbon dioxide over molar mass of ammonia. Right. Now I can substitute in. So we have 12.6 seconds, and we're going to multiply that by square root of 44.007 divided by 17.031. All right, so let's do that then. 44.007 divided by 17.031, 2.583. Take square root of that and multiply that by 12.6. I get 20.25, which again, the new rule for 0.5 is that you round to the even number. So 20.2 seconds. And that's it for chapter 18. Now, I'm going to have the next video, I'm just going to go through what's going to be on the chapter 18 test versus the chapter 19. And then I have like 3 additional practice problems. And the video will show you where to find practice problems if you need them. Thank you very much.